So coulomb, C-O-U-L-O-M-B. So joules per coulomb. So cell potential is referred to or is denoted with an E or E naught. If you have the naught there, then that means it is under standard conditions, which is a 1 molar solution, or it will be 1 atmosphere, and at 25 degrees Celsius. And cell potential is just what you'll also hear called EMF, electromotive force. So that's how much push we have per unit. Okay? So the bigger your E, then the more inclined to be reduced.
Do you think of cell potential as potential difference? Because I always say potential energy rather than...
Potential difference, yes. It'll be the difference of our cathode and our anode. That's our cell potential. So what we're going to do is we're going to have these. We're going to take our reactions and we're going to put them into half reactions. If we flip a reaction, then what we're going to do is we're going to flip our E. What's different from what we've been talking about in thermodynamics is when we multiply our reaction by an integer so that we can get it to be equal, balanced, our E remains the same. E will not change. If I multiply the reaction by 15, E is still going to be the same. All right, because it's push per unit. So if it takes 4 of me to push a box, if it takes 1 of me to push 1 box, and it takes 4 of me to push 4 boxes. So push per unit. Galvanic cell, when you hear the word galvanic cell or voltaic cell, it is spontaneous. It is spontaneous in the direction that gives a positive E. So positive E is spontaneous or thermodynamically favored. Yes?
Reaction being reversed, the sign is reversed, the sign being like positive, negative, it's not going to be like a flip fraction,
right? Right. Yeah, so if you're looking at these reduction potentials, the pink thing, so if you have, say, go all the way down to lithium, then lithium would, if it was needed to be flipped, it would be positive 3.05. Okay?
So it would never be multiplied,
It would, yes.
Okay.
We're only flipping signs on these. Okay, so these are thermo-favored. Negative E is non-spontaneous. So a negative E, when you go to the grocery store or Walmart and you buy a battery, you get a 9-volt battery. It's not a negative 9-volt battery, okay? So if it's a negative, then that means we have to have an outside electrical something to get it going. It needs an outside source. Any questions on that? Yes.
So you said you need the outside source to get it going if it has a negative?
Mm-hmm.
And we're talking about batteries?
We're talking about a cell, if you have a cell. If it's a negative, then it's not going to be spontaneous. It'll need something to push it to go the other way.
So this can be, but can this be applied to batteries?
These are batteries.
Okay, so is that why whenever something asks for a battery and it comes with a charger, it's negative?
Or does it just get less positive? And then you have to recharge it.
Okay.
Yes. Hold on, let me pause this. Let's do an example here. So here is an example. We're given this example, and what I like to do is I just kind of, you have the step-by-step there, but I want to go ahead and go to a page where I don't have the step-by-step. All right, so I'm going to work the example over here, and then you can go back to the step-by-step if you need to, okay?
So
So you can just cross this page out, or cross it out, and you can work it there if you want.
Cross it out.
Yeah, I'm not going to. I promise, I'm not going to. I crossed it out in the last class. I promise. We're not going, because I have another one on the next one. Okay. Omit. All right. So here's our example. We have Fe3 plus copper, and we have copper 2 plus Fe 2 plus. So that is the reaction we are given. So what we're going to do is we're going to split it into its half reactions. So Fe 3 plus goes to Fe 2 plus. Balance your irons. It's good. Balance your hydrogens, oxygens, no hydrogens. So now we balance our electrons. So we need an electron on the left side. Now we do the same thing for copper. And by now you should realize if you're adding electrons to one side, if you're balancing it right on the other side, then the electron should go on the other side. So we need 2 electrons here. Everybody good with that? All right, so go to your reduction table. So these are reduction tables. So all of these are where the electron is being gained. So go in and see, iron is one where there's Fe3 plus and there's 2 plus. So we have Fe3 plus, and I have it as 0.77. You guys see that?
Yeah.
All right. So it is 0.77 volts. Now go find the copper 2 plus. And
Weird.
0.34. So what we're going to do, so it's copper 2 plus 2 electrons, right? So it's 0.34. It's 0.34, but it's flipped, so we need to have it as negative 0.34. Y'all are getting ahead of me. When I get negative, do that, and I subtract them, what do we get? 0.43 volts. That is our cell potential.
Don't we subtract negative 30.34, so it's
We're adding these. Okay, so this is what's going to confuse you. If you flip your sign, like I do, everybody listening, if you flip your sign, then what happens is you add your 2 potentials together. If you're not messing with your sign over here, then you're just subtracting, right? So if we just wouldn't have looked, if you just want to look at this and just subtract, you can, or you can flip your side and add. It's whatever you want to do. Does that make sense? If you're using it straight off of here, you're subtracting. So we take 0.77 minus 0.34.
So you could like add the negative number.
Yeah. Is that what we're doing?
So either way is this.
Wait.
Or you add, or you flip it and you add.
But, okay.
She's saying because on that they're all going to be positive zeros.
But they're not all going to be positive. They're down here.
Either
So,
way you
but-
add. No. Okay, it's okay. I don't get it. So you just add the
We're
negative.
adding, but because it's a negative sign, we're subtracting.
So you add the negative number.
Yes.
So either way you add.
Yeah. It just ends up being a smaller number because the number is negative.
However you want to look at it. Because, but the problem is if you're looking up here and you're looking at, say, iron and cobalt, you wouldn't be. If you're using them straight off the chart, you subtract. But if you flipped it one, then you add it. Hold on.
So you're
Now that we're all confused. All right, so if we go over to this number 3, it says which one of these is the strongest oxidizing agent? They don't use the word oxidizing agent in the AP world anymore. So we're going to put which of the following is most or more apt to be reduced. So what we're going to do is we're going to go find your E values for each one of these. So you're going to have to use the chart that is in your note packet. So go to the chart. It's like right before page 31. And find me the values for these, for MnO4, Br2, and Ca2+.
Is it the result?
I want the volts, the potential.
Are those the result of the thing? Like, if we were going to make this.
We're just, you're just,
she means like
well, straight off the chart. What's,
Supposed to look at on the chart, I guess.
you're looking on
Or
the,
the letter.
where the, what's going to be reduced, which means it's going to have to gain electrons.
So I should look for MnO4 minus on the left side?
Yes.
$1.51.
1.51 volts. Somebody go find Br2, somebody go find Ca2+.
CA2+ is negative 2.84.
And then 1.065.
1.065. Okay, so which one is more apt to be reduced? So the one that has the largest number is going to be the one that is more apt to be reduced. So permanganate is going to be the most apt to be reduced. It has that higher potential. It's more likely to get those electrons up, easier to get those electrons up than it would be for, or to gain electrons.
Because it's positive.
there's no
It was,
There is an I said you have to go to your packet to look for that number.
Oh.
it wants to become closer to neutral, right? Or closer to as most negative as it can get.
It's just because of that value, it's more likely to gain electrons.
Or the biggest positive.
So the biggest positive, the more likely it's going to gain electrons.
What are these numbers mean exactly?
It's the cell potential.
It's the
So it's the potential to get more electrons, that's it, right?
Yes.
So high potential means it's more likely to get electrons?
The higher your number, the more likely you are to be reduced, which means the more likely you are to gain electrons. Okay, so let's go work another problem. Will aluminum displace copper 2 ion from an aqueous solution of copper nitrate? So this is a single replacement. I want to know if aluminum can kick out the copper 2 nitrate and become the ion. All right, the nitrate I took out because it's a spectator. It's not part of the redox. So the next thing I do is we're going to get your half reactions. So copper 2+ and copper means I need to add 2 electrons as a reactant. Then I have aluminum to aluminum 3+, and I have 3 electrons. So the copper is the one that you're going to find on the reduction because it's the one that's being reduced. Yes?
I know you just finished this, but I'm kind of confused. So it says, or I'll just wait till you finish, but then I'll ask. I'm so confused. I'm sorry.
Okay. So on the table, where is copper? What's its value? 0.34. Now go to the table and find aluminum and tell me what aluminum's value is. It's negative 1.66, but we flipped it, so now it's going to be positive.
And then add.
Now, it doesn't say to atom or anything. It doesn't say what is the value of your cell potential. It says, will this occur? Is it a positive or a negative? It's a positive. So, yes, it will occur.
Because it's thermodynamic.
So it's thermodynamically favored. If it would have been a negative, then it wouldn't have been thermodynamically favored. So then the last step, you've got to balance it, the equation. So we're going to have 3Cu2 plus 2Al gives me 3Cus plus 2 Al3 pluses. Okay. All right. Magnesium. Will magnesium displace 10(2) from an aqueous solution of 10 nitrate? So break it up into its half reactions. You have Mg going to Mg2 plus, which means I need 2 electrons. And we have Sn2 plus going to Sn, and we need 2 electrons over here. So if we go, we're going to look at 10. 10's the one that's being reduced, so we need 10(2) plus. Negative 0.14. And we go to magnesium and find magnesium on the chart. Negative 2.37, but it's flipped, so it's a positive 2.37. How do we know which one is just how it is? If it's not on here, exactly the way it is that you've written it, then it's flipped.
Okay.
So it is this a yes or no?
Yes.
Yes. So yes, this is thermodynamically favored. Which means yes, magnesium will displace it. I mean, this is really good, like real life things is if you have something like the copper nitrate when we did the bullet lab, do I want to store some aluminum in? Do I want to store it in an aluminum can? I don't want to store it in an aluminum can because the aluminum will displace the copper and spring a leak.
Wait, do we need to balance it?
Oh, it is. I just flipped it and I lost my page. So it's already balanced. It just should be Mg plus Sn2 plus produces Mg2 plus Sn.
Why did you do it on top?
Just to make sure that you're right. What? What did I do? I multiplied the top by 2 and the bottom, or by 3. All right. in the next one it'll, not this one, but the next one well, this one will balance out okay, but the next one won't. So we'll go through that. Okay. All right, guys, let's go. Number 6 says calculate the E naught and determine if it will occur. So, and balance equations in an acid solution. So go ahead and break it up. We have Pb goes to Pb2 plus, which means I need 2 electrons. We have Cl2, which goes to Cl minus. Balance your Cl's. And then we need 2 electrons over there.
We had 2 electrons because of the coefficient of the negative, or the 2 negatives. I said that wrong.
Yes.
What? It's -2 and it's -2.
Yes.
The lead's 0, the other one's a 0.
So you can't even out to be 0.
You even them out to get, yeah, they need to be the same charge. Okay. So we end up with Pb plus Cl2 produces Pb2 plus 2Cl minus. All right, so go to the periodic, or to your standard reduction. Find chlorine as it has been written. I have 1.36.
And that is the one that's flipped, right?
Lead is the one that's flipped. So find lead.
Is there always going to be one that's flipped?
Yes.
Yeah, it would be positive 0.13 negative.
So it's a negative 0.13, but where we flipped it, so it's positive, for a total of 1.49 volts.
So yes.
So yes, it occurs.
And on the AP question, is that all? If it doesn't ask for anything else, we would just say yes, it occurs.
Yeah, you would say because the E cell is a positive, it would be thermodynamically favored.
Okay. But if it was like, are these usually free response questions?
These are usually free response questions.
I like.
All right.
That's just free response questions. You can kind of like push your way through it.
Hey, listen, and when we're going to this next one we do, you're going to need the one in your packet, that table in your packet. But when we're doing these, these are balanced equations. How they, if you're balancing and you're having a trouble balancing them, go to that chart and see how it's balanced.
Are we gonna have this chart?
Yeah, you'll be given.
On the AP test, will you give us?
Yeah, that's what they just asked. You'll be having a chart. Okay, last one. Mn2 plus. So let's break it up. So Mn2 plus goes to MnO4 minus. So we need to balance our Mn's. That's good. Balance your oxygens by adding 4 waters. Now we balance our hydrogens by adding 8 hydrogens.
And that's not okay.
So then you should go on your chart and see if you can find that. I don't think it's on the pink one. Oh, no, and we need the electrons. I have 2 and I have 7, so that means plus 5 over here. All right, so then go find that on the thing. 1.51. Oh, stop. Oh my gosh. So this is 1.51 volts. Now we go and do the same thing with dichromate. Oh, it's negative?
Yeah.
We go to dichromate, Cr2O7, 2 minus. And we get Cr3 plus. So balance your chromates. Put a 2, or your chromiums, put a 2 there. Now we need to balance our oxygens. So we need 7 H2Os. And then we need to balance our hydrogen, so that means we need 14 H's over here. So I have 14, and so I have 12 plus and a 6 plus. So that means I need 6 electrons over here.
Well, so electrons always work out to where they're on opposite.
Yes, they will. Your electrons should always work out to where they're on the opposite sides.
That's why I need to.
Okay.
It's 6 electrons.
6 electrons. So then you go and find that equation on the chart. 1.36. 1.36. And we're going to add those. So what is our E cell here? It's what? Negative 0.15 volts. So is this thermodynamically favored? No. Because we have a negative cell potential. And then our last step is to go back and balance it, which is going to be so much fun. So I'm going to multiply the top everything by 6. So this becomes 24. This becomes a 6. This is a 6. This is a 48. And this is 30. 6 over here becomes 30. 14. So I'm multiplying by 5. So now it becomes 70. Then I have a 5 here, a 10 here, and a 35. 35 there. And then go clean it up. So waters over here go away, and we're left with 11 waters. So we have 6 Mn 2 pluses plus, let's see, 70 H pluses minus 48. 22? So 22 H pluses plus 5 chromates, dichromates, gives me 6 MnO4s plus 10 chromium 3 pluses plus 11 waters. When you get something like that, spot check it. Make sure that it's all balanced. 22 H's. I have 35 O's. 20, wait, is it 35? Oh yeah, 24. Oh yeah, there we go. And that is how you do that. Any questions on that? Okay, so now we're going to go one step further. We're going to ignore the line notation real quick, and we're going to talk about our galvanic cell. So our galvanic cell, our electrons are going to flow from our anode to our cathode. Okay, anode is the one that is being oxidized. Cathode is the one that's being reduced. So your anode gets skinnier while your cathode gets fatter. Okay? Anorexic ox and fat red cat.
Not where my mind is going. Okay.
Oh my goodness, now I know from that quote.
So anorexic ox and your fat red cat. So what we'll have is you need to be able to designate your anode and your cathode. Tell me which way electrons are flowing. Tell me what the E potential is. And we will have like an inert conductor in there if needed. So we're just going to sketch one of these real quick and then be done. We have here, it says sketch a cell using the following solution. So we have a silver electrode in, so I'm going to just go ahead and draw my silver. Oh, there's my solution. There's my silver. So that's my silver. And then I have silver ions out here in my solution. And then we're going to do the same thing for our copper. So here's our copper. And we have copper 2 pluses floating out here. So the next thing you need to do is you need to go to your chart. So go to your chart and find copper solid and copper 2 plus, and then find your silver solid and your silver plus one.
They're both.
Oh, they're the other way on the period, yeah. So 2 plus 2 electrons gives me Cu, or if we have Ag plus 1 electron gives me Ag. So what is the value for Cu? 0.24? 0.34. What's the value for silver? On our chart, what's the value for silver? 0.8. We're going to flow from the least to the biggest number. So how are we going to flow? We're going to flow from copper to silver. So I'm going to put my wires here. I'm going to put my electrons, and I'm showing electrons are flowing the other way to the anode, or sorry, to the cathode. So silver is my cathode, while copper is my anode. I usually like drawing these the other way, so the electrons flow from left to right, but as long as you're showing which way electrons are flowing. Okay? So what is our cell potential then? We have 0.80 minus 0.34. So it's 0.46? Wait. We had 80 and 34, right? Mm-hmm. Okay, so 80 is the biggest one. And then we have to flip the other one. So it would be a negative 0.34. Because right now they're both running as reductions. One of them has to be oxidized.
So you just put this one?
So you slip the smaller number. So it would be 0.46.
Wait, so if one of these were already negative, would we have to flip?
Hold on.